we want to find the derivative for the following. We have y equals 3 over x plus 5 sine x. Okay. Anytime I find the derivative, I want to be able to really see all the exponents. So I want to write this really as y is equal to, instead of 3 over x, let's write it as 3x to the negative 1. So just like I said, so we can really see all the exponents. And then plus 5 sine x. Okay. So from there, if you either want to write dy dx, or if you want to write it as y prime, same difference, is going to equal, if you want to pull out the 3, and then you just have to really kind of focus on just taking the derivative of x to the negative 1. So it would be negative 1 times x to the negative 2. And then plus 5, if I pull off the 5 off front, just think about now that I'm just taking the derivative of sine x, and the derivative of sine is cosine x. Okay, so cleaning it up from here, we have negative 3x to the negative 2 plus 5 cosine x. And if we didn't want to leave our answers with any negative exponents, then we can write this as negative 3 over x squared plus 5 cosine x. And that would be our answer for this first problem. Okay, so let's go on to the next one. All right, in this example, in part B, we have y equals 2. And then I want to write it as, if you look here, you have x, you have our independent variable x in two different spots. Or they're connected through multiplication. So I really want to write it as a product as x squared and cotangent x, but you really kind of have two parts there. And then of course we'll write this one as x to the negative 2. So when I come in here to get the derivative, or y prime, and I've got the product rule that I've got to do with this pairing right here. So it's going to be first times the derivative of the second, which is negative cosecant squared x, plus the second times the derivative of the first, so 2x to the first, and then minus, drop down that negative 2 and subtract 1 from the exponent. Okay, finishing cleaning this up a little bit. So y prime is going to be a negative x squared cosecant squared x, plus, we'll go and leave 2x in the front, times cotangent x, and then plus 2x to the negative 3, and just, if we want to write this just one more time, so we don't have any negative exponents. And I'm kind of inclined to not write negative exponents, especially if the problem was given to you without negative exponents. But technically we do have kind of the same answer either way. And there is the final answer for part B. Okay. Moving on, let's go to part C. In part C, what I'm kind of looking at when I look at this, okay, I've got a product of two things. I've got sine x and cosine x, and then I have secant x. And I'm thinking that before you even get started with this problem, we really might go about cleaning up the function first and seeing what we can get, and then we'll go through and take the derivatives. Okay, so sine x times secant x plus cosine x times secant x. Well, sine times 1 over cosine, that's just tangent of x, and cosine x times secant x, this is cosine function times its reciprocal function. Those all together will just give you 1. So now, instead of having to take the whole product rule, I don't have to worry about it anymore, because now I just have tangent x plus 1. It makes it a lot simpler. So dy dx, or y prime, is going to be the derivative of tangent, which is secant squared x, and the derivative of 1, which is 0. So we can write this as just secant squared x and call part C finished. All right. Kind of the same thing here with D, is before I even get started, because I'm not going to want to have to do the quotient rule on that one and the quotient rule on that, since we have both variables in the top and the bottom, top and bottom. So having to do the quotient rule, why don't we go about cleaning up the function first? So we've got two fractions. If I want to bring them together, let's get a common denominator of x cosine x. And then in the top over here, we're going to write that then as cosine squared x and x squared over there to get a common denominators. Okay? Combining them together, we have cosine squared x plus x squared all over x cosine x. Okay, so now looking at this, the question is did it make a difference? By having us clean this up a little bit, or quote unquote bringing these terms together into one fraction, did that really help us at all? Well, Yes and no. It's one of those that up here in the top, I just have to take the derivative of cosine squared x, and then I just have to take the derivative of cosine x, or I mean of x squared. Here in the bottom, I've got the product rule, and then all of this is inside of the quotient rule. So I'm thinking that that didn't help, but it's always a good thing to check. So why don't we do this? Let's go back to the original problem the way it's written, as cosine x over x and x over cosine x. And let's just see, let's go and start trying to do the derivative here and see if it gets out a little bit easier before we come back to this guy and see what we can do. Okay, so it would be the bottom times the derivative of the top, which is negative sine x, minus the top times the derivative of the bottom, all over the bottom squared. Okay, plus, and then the second one. So bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Well, look how both these fractions that we're going to be adding together both have a denominator of x squared, so that means I can actually pull them together. So y prime is going to be a negative x sine x minus cosine x plus cosine x plus x sine x all over x squared. So a negative cosine x, a positive cosine x, a negative x sine x, a positive x sine x. So we're really looking at 0 over x squared, which is 0. So the derivative for this function is actually 0. And had I found it through this other way, you would have gotten the exact same thing. Just seems like it turns out a little bit easier going through just the original method. But it's always good to check, just in case. Okay, moving along, let's go to our next example, example 2. We want to find, instead of just dy dx, we change our variables up a little bit, but you're going to see it's the exact same thing. We want to find, always your dependent variable is what's on top. So we're taking the derivative of s with respect to t, and t's are independent variable over here on the right, so that's good. All right, so either if you want to write it as ds dt, or s prime is going to be the bottom, so 1 minus cosine t times the derivative of the top, which is cosine t, minus the top times the derivative of the bottom. Well, the derivative of 1 is 0, minus, and the derivative of cosine t is a negative sine t. Okay, kind of notice how I pay attention to the signs there. I want to make sure I get everything in there. Get all my negative signs if I need them. And then all over the bottom squared. Okay. Now notice I didn't write that as 1 minus cosine squared t. I did 1 minus cosine t, then all of that squared. Total different answer otherwise. Okay. So coming through, now cleaning up, we get 1 minus cosine t times cosine t. And my initial reaction is to maybe not multiply those yet. Might need them to, but I'm just going to hold off for just one more step until I maybe see something a little bit more. Okay. And then this is saying a negative sine t times 0 is 0. A negative sine t times a positive sine t will be a negative sine squared t. Okay, down here in the denominator, we'll have 1 minus cosine t and 1 minus cosine t. All right, so now let's finish cleaning this up. It looks like there in the numerator, I'm going to want to go ahead and actually multiply that out. So s prime is going to be cosine t minus cosine squared t minus sine squared t, all over 1 minus 2 cosine t plus cosine squared t. Okay. Okay, well, finishing up here in the whole, our goal here is to probably try to cancel out some terms in the top and the bottom. And the only way that I can see that we're going to have this, I'm recognizing something happening with these last two terms here. Maybe you guys see it too, is that if I pull off a negative from those two terms, I get cosine squared t and a sine squared t. And then, of course, down there in the denominator, well, cosine squared t plus sine squared t, all of that goes away and I get a 1. Okay, so now let's analyze this. What's in the top is a cosine t minus 1. If I went back to my old denominator before I multiplied it out, do you see how we almost have the exact same thing? So let's write it like that. Let's go cosine t minus 1. Let's put our denominator back to where it was, which is 1 minus cosine t and 1 minus cosine t. And then just realizing, since cosine t minus 1 and 1 minus cosine t, what they are, they're opposites. What happens is when they cancel off, they don't leave behind just a positive 1. What they leave behind is a negative 1. So the answer to this really is negative 1 over 1 minus cosine t. Okay? And if you want to write it like that, that's great. Some other way you might also see it is that your inverse function, or I'm writing inverse function, but your derivative for s is actually, if you want to write it like this, if you want to distribute the negative from the top, you can write it as 1 over and then switch the signs in the bottom instead. And that would have been the exact same answer. Okay? So whether you wrote it like this or you decided to take that negative and kind of distribute it throughout it and get the 1 over here on the left, it's the exact same thing. Okay, let's go on to example 3. Here in this example, we kind of want to analyze what they're asking us to find. We're taking the derivative of r with respect to theta. So theta is like our x, okay, and r is like our y. If we look to the actual function that we're going to do, so it's like y equals, and then see here's our x, here's an x, and here's an x. And it's good to look at that because what's going to happen here is we actually are going to have to take a product rule because it's theta times sine of theta plus cosine of theta. Okay, so now dr d theta, or r prime, is going to be the first times the derivative of the second plus the second times the derivative of the first, and then plus the derivative of cosine, which is negative sine theta. Okay, keeping on with this, we have theta cosine theta plus sine theta minus sine theta. So canceling out those two terms, we just get theta cosine theta. And of course, that one was a little bit easier than the last one. Example 4.